of your expertise is the tiger stripes on Enceladus, right?
Yeah, I mean, again, that was a little bit of I like to dabble in a few different areas.
Uh-huh.
Yes, but yes, I did write a paper on the tiger stripes of Enceladus. Yeah.
So could you give, for the audience, just a brief explanation of what these tiger stripes are and kind of how they're formed?
Yeah. So first of all, Enceladus is a tiny moon of Saturn. It's about 500 kilometers across. But I would say it's arguably one of the most interesting places in the solar system because it is, even though it's tiny, it's extremely geologically active, which is very surprising. So it's the brightest object in the solar system.
Oh, wow.
And we knew this from the Voyager flyby that it had a very young looking surface. There's like very few craters, a lot of old moons sitting out there, just nothing but craters. That's all that happens to them is they get hit by stuff. But this thing has a very young surface, vast regions of the surface where there's no craters, and there's these tectonic features suggesting that there's been some kind of geologic activity, some modification of the surface. So if it's geologically young, what is going on? How is this tiny thing active? And then when we got there with the Cassini mission, you could see, well, I think even with Voyager, you could see these tiger stripes. So this, notably at the South Pole, there's this series of fractures. Actually, I'm not sure if they saw them in Voyager or not, but certainly with Cassini, we have like imagery of these, there's kind of fractures all over the place, but there's this very prominent set of 4, or depending on how you count, maybe 5 fractures at the South Pole of Enceladus. And what's more is that with Cassini, you started seeing not only evidence of this thing being young, but actually being active right now. So there's water spraying out of these fractures right now. Like about 200 kilograms per second worth of water ice is coming out of these fractures.
Sheesh. Yeah.
And it just, some of it goes into orbit around Saturn. A lot of it just ballistically falls back down onto the surface of Enceladus. And that's why it's so bright, because it's essentially covered in its own fresh coating of snow.
Gotcha.
Yeah, and so with Cassini, we have a bunch of different kinds of measurements of this. There were disturbances in the magnetic field. There was a few other different things. But you could actually see with imagery, once they had the flyby geometry right, you could image it so that they were backlit by the sun, and you can actually just see these plumes of erupting material coming out. Wow. Yeah. And then later, they organized some of the flybys so that the Cassini spacecraft actually flew through the plume of erupting material and sampled it with a couple of different instruments. They had a new ion and neutral mass spectrometer, and they had another thing called a cosmic dust analyzer, and both those were able to take samples. And so we know a bit about what those things are.
Instruments that take a physical sample,
right,
and then through some fancy geochemical process or just like chemical process in a machine, tell you the concentrations of different elements.
Yeah, basically. Okay. So they weren't designed for that. They were designed to pick up stuff that's in the space environment, but they never expected that there was going to be this high density spray stuff spraying out of a moon. But let's go see what it tastes like. And anyway, so we know that it's water ice. We know that it's rich in all kinds of salts, and we know there's organic molecules there. We know even like large complex organic molecules. We just don't know what they are, because they get smashed up in the detector. So you don't know what, basically you can count the mass and you can figure out that it was a large complex organic molecule, but you don't know if it was like alive or not. So maybe with a future mission, you could go back with a different combination of instruments that are designed differently and actually figure out whether that material is biological or not. Right now, we know it's interesting, but we don't know whether or not it's biological.
So through that mass spectrometer, how much carbon, how much nitrogen, how much oxygen, so you can guess which compounds this could be, but you don't know the actual arrangement of.
Yeah, I think that's right. Yeah.
That. Okay.
Again, that's not my expertise, but I think that's right. Yeah.
Okay, gotcha.
Yeah.
So, from my understanding, these tiger stripes are caused by.
Oh yeah, I didn't explain that yet.
Yeah, you're all good. Now's your chance.
Okay, shall I?
So the eccentric orbit of Enceladus, right?
Yeah.
Yeah.
Well, okay. So first of all, we don't know how the tiger stripes are formed, but I can tell you some theories, including one theory that I suggested. Yeah. So first of all, I should explain what you're talking about with the eccentric orbit. So how do you put any energy inside this body in the first place? And the only way you can really do it is it's so small that there's no source of energy inside. There's not enough radioactive elements to keep it warm inside. So the only way that you're keeping it warm inside is through something called tidal heating. And that occurs because, like you said, the orbit is eccentric. So sometimes it's closer to Saturn, sometimes it's a little bit further away. I mean, there's a closest point in the orbit and a furthest point in the orbit. It's this elliptical orbit. And so that means that the tidal forces, which is the gradient and the gravitational force from Saturn, is stretching the body out, and then it's stretching and relaxing and stretching and relaxing. And so if you're stretching and relaxing something, like if you do that with metal, like it gets warm and soft, right? And so it's the same with ice. If you get the right sort of time scale and the right temperature, the ice behaves viscoelastically on that same time scale as the orbit. And so that means you are straining it. And so there's some basically friction inside the system, and that's heating it up.
So viscoelastically, kind of the same way an aluminum can would behave, where you kind of bend and but it's more almost like viscous, more like almost like a liquid, right?
Yeah, it's somewhere in between. Like if it was purely liquid, it wouldn't do this, and if it was purely elastic, where it like completely recovered all the energy, then it wouldn't do this. But if it's somewhere in between, then there will be strains that actually dissipate energy. Okay. And so essentially, what you're doing is transferring energy through the gravitational interaction between Saturn and the Moon. This is true of all pairs of bodies in the solar system. You're transferring energy between them, and in general, like, it's energy that's coming out of the rotation of Saturn. It's basically taking some of its rotational energy, but don't worry, there's plenty, and depositing it inside the moons of Saturn, and they're dissipating energy and turning it into heat. And so that's keeping it warm inside.
So rotational energy being the spin of Saturn? Or
yeah, you're slowing down the rotation rate of Saturn.
Oh, wow.
Yeah. It's the same as the Earth and the Moon interaction, right?
Yeah.
So the Moon is getting further and further away from the Earth, and the Earth's rotation rate is slowing. And that's what's happening. It's like you're taking rotational energy from the Earth and you're putting it into the orbit of the Moon. Actually, that's a slightly different thing, but but they're sort of related.
Or and then the Moon is putting energy into the Earth through stretching and straining, and the Earth the same way, right?
It's also doing that, but yeah, it's not in terms of the orbital evolution. What's happening is the angular momentum from the Earth is being transferred into the Moon. And so, but yeah, you're right that there's also interactions that cause, like for example, the tides, and then that gets dissipated, the ocean tides, because the land and the water respond differently. You end up with all this friction and waves smashing into things, and so there's a bunch of energy dissipated that way on the Earth. Yeah.
Okay. Yeah. Okay, so sorry.
Yeah, no,
Put you on a tangent.
This is going to happen all the time.
Back to Enceladus.
Yeah. So I still didn't explain the tiger stripes at all. So we don't know how they form, but one idea that a colleague of mine had a number of years ago was that if there's some period in the history of Enceladus where it's freezing, like there's net freezing of the ocean, what happens is as you're freezing, the ice takes up more space than water. So basically there's a volume change there. And so now you're squeezing the ocean and you're putting the overlying ice shell into tension. And so as you gradually thicken the ice shell and freeze the ocean, you basically build up stresses in the ice shell. And at some point you will reach the failure threshold where the ice shell will crack. Now that gives you one fracture, but that doesn't give you and also why it should be at the South Pole or why it should be at one of the poles. That's
another question I was going to ask.
Yeah. This paper tries to answer all these questions at once. But one idea is that because of this tidal heating, I didn't explain this, but the tidal heating where the friction is happening at the bottom of the ice shell, that is maximum at the poles. And it's not obvious why, but it's just like a geometric effect that's where the maximum strains occur. And so that means that the place where the tidal heating is maximum is at the poles and it's minimum at the equator. And so that means that the ice shell is going to be thinner at the poles and thicker at the equator. So if you're building up stresses through this freezing, then at some point it's going to fail. And where is it going to fail? It's going to fail where the ice shell is thinnest, because that's where the stresses are going to concentrate. And so it's going to fail at one of the poles. And I think it's a 50-50 chance whether it's the North Pole or the South Pole. But once it happens, then that overpressure on the ocean is relieved. And so that mechanism is done. That is no longer available. You just made a fracture at one of the poles. In this case, it turns out to be the South Pole. That still doesn't explain why you get the rest of the fractures. So then the additional idea with that paper was that once you're erupting, once you make that fracture, now what happens is water fills up that crack to the level of neutral buoyancy. And at the top of it, it's exposed to the vacuum of space. So now that water is just boiling off. And there's people who've done research on that, like how do you keep it in a controlled state so that it's, there's enough back pressure to kind of stabilize the system so it doesn't just like freeze over. but you can have a steady ongoing eruptions for a long period of time. But all that stuff, some of it goes into orbit around Saturn, but most of it, like I said, ballistically just comes back down onto the surface. It snows back down onto the surface. And preferentially, that erupting material piles up on the flanks of that newly opened fissure. So if you can imagine, you have this elastic plate, now it's broken, and now you're piling stuff up on the edge of this elastic plate. And so that's causing bending. Mm-hmm. And so this is the idea of that paper, was that this is going to create bending stresses in that elastic crust, that ice shell. And at some point, and it turns out for very reasonable assumptions about the elastic properties of the ice shell, the maximum bending stresses occur 35 kilometers away, which is the spacing between the tiger stripes. So this is a way of explaining so the questions, to come back to summarize them, like how did the tiger stripes form? Why are they only at one pole? Why are they 35 kilometers apart? Why are they in parallel sets? And why don't you see them anywhere else in the solar system? So I've explained some of those things now. So the first one, you get from this ocean overpressure maybe. But once you do that, now you start creating bending stresses, and that's why you get one fracture right through the South Pole, that's Baghdad, and then you get a symmetric pair, 35 kilometers out on either side of that, are Damascus and Cairo, the names of these things. Mm-hmm. And then once they erupt, or once they open up, then stuff starts erupting out of them, and then the same thing happens. Now they build up a load on the end of that now broken plate, and then they create another set of fractures, and so on. So you get this kind of cascading series of fractures away from the pole.
Do the fractures decrease in size as you move outward from your progenitor?
A little bit. But another question is, they also stop at some point. So why do they stop? So, it could be that at some point you get far enough away from the pole that the background ice shell thickness is too big for the fractures to get all the way through. Maybe as the erupting material gets spread out over more and more open fractures, it's just not building up fast enough for it to kind of build up those loads before it can just relax away. So I don't know exactly why or how it stops, but those are a couple of ideas. But I didn't explain why it's only Enceladus, and that's actually the most interesting part.
Yeah. Why is it not Europa or other icy moons?
Yeah. So what I've told you is that I'm creating bending stresses, but what happens is when the fracture starts is now the bending stresses have to concentrate in the remaining unbroken part of the ice shell. And so as the crack propagates, the bending stresses at the crack tip increase as you go. But at the same time, you have overburden pressure. As you go deeper and deeper, into the Earth or into any planet, there's more and more pressure. The weight of all the rock or ice is squeezing you more and more. And so those two things are working against each other. But on Enceladus, the gravity is so small that overburden pressure is essentially irrelevant. So the crack tip stress just rapidly increases. So the crack just rockets all the way through the ice shell. Whereas if you go to like Ganymede or Titan or Callisto, one of those bigger ones, you could in theory have the same kind of mechanism where the bending stress starts a crack, but as soon as the crack propagates a little ways down, the overburden pressure stops it. So it just stops and it never gets going. And even if you could eventually keep building up the loads and propagate it little by little, eventually you get to the ductile part of the ice where the ice is warm and soft, and this is not going to work anymore. So you have to do it quickly on the time scale when the ice shell is behaving elastically, and that only works on small bodies like Enceladus.
Wow. So that icy crust is thin enough to where you can have that brittle kind of like cracking open, whereas because your pressure conditions are such, because it's smaller than these larger icy moons that have that kind of brittle ductile transition.
Yeah, I mean, it's mostly just because the gravity is bigger on. So it's kind of a function of the shell thickness and then the gravity. So gravity is so big on those bodies that the overburden, the pressure increases so quickly that it's going to stop the crack from propagating. Whereas on Enceladus, it doesn't.
So why is there so much pressure to where the water on Enceladus like bursts and spews out of these tiger stripes?
Yeah, so I don't think you need pressure to do that. It could be that it's just like I was saying, once you open the fracture and you're exposing the water to the vacuum, it's going to boil off just into the vacuum. Mm-hmm. So it's this concept of a controlled boiling that's sustaining these eruptions. It's not that there's pressure squeezing the ocean anymore. That's the idea for the first fracture, like how you make the first fracture. But once you do that, that overpressure is gone. Mm-hmm. And so you don't need overpressure anymore to keep those eruptions going.
And boiling. So, is it hot at the surface, or is there?
No, boiling just because there's no atmosphere, so the pressure is so like if you
There's no like
like
in a
it,
container. There's gas on top of that water in that container, so so that those liquid molecules don't evaporate off.
yeah, like if I have a cup of water here, even if I don't change the temperature, if I lower the pressure enough, it will boil.
Gotcha.
Right.
Yeah.
So the water boils at a lower temperature in the mountains.
Mm-hmm.
It's lower pressure.
Gotcha.
Yeah. The phase diagram for water is kind of complicated, but yeah, pressure is important. Mm-hmm. So if you lower the pressure enough, yeah.
Gotcha. And so because I remember reading somewhere that Europa has kind of geysers spewing out, but I can't imagine to the scale of the tiger stripe. Is it the same mechanisms going on there, just smaller scale?
The observations are pretty limited. They're from, I think, the Hubble Space Telescope. Mm-hmm. So it's not from close-up observations, but there's a couple of detections of what looks like eruptions of some kind of water from Europa. Mm-hmm. When we go back there with Europa Clipper, hopefully we'll see some of that evidence. It doesn't seem to be anything like as intense as Enceladus. It's not like Enceladus is continuously erupting. There's some modulation in it, but it's basically continuously erupting for the whole, ever since we started watching it in like 2005. So Europa seems to be maybe less active, but it might be somewhat active. Maybe it's enough that once we're there watching it for a while, we'll see something. But I don't know. So whether it's the same mechanism or not, it's hard to say.
So in these icy moons,
we don't even know what the mechanism is on Enceladus, really. I told you some ideas, but we don't really know. Yeah.
So on these icy moons, how much knowledge do we have of the internal structure as far as is there some kind of so you have that icy crust and then you have this layer of ocean, and then under that layer of ocean, is there another kind of more solid rocky crust, or does it kind of, is there more of a direct mantle or core interface between that ocean?
Yeah. So first of all, I guess I should say, how do we know anything about the interior structure anyway? So we know something about the shape, and we know what the gravitational field looks like, and we know how those things are related to the rotation and the radial density structure. And so you can rule out certain radial density structures. You get some idea of how much there's rock and how much there's water, whether it's frozen or liquid. It's hard to tell how much of it's frozen, how much of it is liquid, just from the density structure, because the difference between the density of ice and water is pretty small. But yeah, we know that it's Enceladus, something like 60 kilometer ice and water hydrosphere, let's say. And then underneath that is a rocky core. So the radius of that's maybe 195 kilometers, plus or minus a few kilometers. That's from the shape and the gravitational field. We can figure that out. But we use other things like the libration amplitude, which is something. That's a weird word, but it's it's basically how much it wobbles. So the way the ice shell wobbles tells you that it's decoupled from the rocky interior. Otherwise, it wouldn't be able to wobble that much. It would be more limited. Oh, wow. But so it wobbles around, and it wobbles so much that we think it's decoupled, meaning that there's a global liquid water ocean there. And then also the magnitude of the wobbling tells you how thick the ice shell is. So the combination of all those measurements gives us a picture of the internal structure. But as to what the seafloor looks like I don't think we have a good way of constraining that at this point. And it also depends what you mean by by crust. Yeah, we basically assume there's some kind of rocky core. We don't distinguish between whether there's a chemically distinct layer where there's rock of a certain type and then it changes to a different type. We don't really have the kind of resolution to be able to make those kinds of inferences at this point.
Yeah, I'm wondering how you would even make an inference like that, because you use. I guess seismics.
Maybe seismically.
Yeah. Because radar would go through the ice, but then as soon as you hit the water, it would all reflect, or almost all of it would reflect back up. And even seismic, I'd imagine through an ocean as deep as that, it's going to be hard to carry a wave all the way through and then interpret that, or interpret what it traveled through before it went through that ocean.
Yeah, I don't know how far they've gotten, but there's certainly people thinking about that, what we could do with seismometers on these kinds of bodies. But yeah, if you have an ice shell decoupled from the deeper interior, what your seismic imaging looks like, I'm sure they could do something.
Yeah.
But right now we don't know.
Yeah. And is Enceladus, through the kind of eruption in those tiger stripes, is it losing any significant amount of mass?
Yeah, you can do the math. It's like 200 kilograms per second
Yep.
is erupting, and then like 10% of that escapes into orbit around Saturn. That's what the E ring is. If you ever look at the rings of Saturn, there's these like pretty solid looking rings. They're all just like balls of ice. But then there's this diffuse looking one that's called the E ring. That's where Enceladus is, and so it's actually the guts of Enceladus that are coming out and making the E ring.
Oh, so it's making like a smoke trail as it goes around.
Yeah, but it's kind of like permanently there. Kind of permanently there. And I guess there's some diffusion of that out into wider space. So I'm not sure how much mass loss there is from the system, but if you assume it's like the whole 20 kilograms per second that escapes Enceladus itself is all gone and never comes back to Enceladus, then you can figure out how long it would take to lose a significant fraction of its mass. I've done this before. It's like, it's not nothing, but it might lose like 1% of its mass over the history of the solar system or something.
Oh,
like that.
wow. Okay. So it's nothing